Hi everyone, I'm Yushan, and I'm joined with my teammate Zhongpeng, and we will be talking about how Uber manages flaky tests with Bazel and rules go. So within Uber, we run thousands of tests every day across a very diverse tech stack. You can imagine at our scale that flaky tests can be a challenge. They cause false negatives, they waste CI time, and they also erode developers' trust in the test results. So we built a sophisticated flaky test detection pipeline that basically detects flaky tests, and so we can skip them in CI. However, the story doesn't stop there. As more and more tests get skipped in CI, the less and less production code gets covered, and this results to risk of more and more bugs slipping in. So we need a separate process where developers are encouraged to fix their flaky tests, but also prevent new flaky tests from slipping into our main branch. So as an overview, we're going to go over the background, and we're going to talk about how we report these flaky tests, how we filter them out in CI, how certain teams may want their flaky tests to run regardless on their PRs, regardless of the flakiness, and strategies we use to fix test timeouts. Right. So Uber's monorepo model allows one primary language per repo. Despite the separation, all the repos follow a similar process. Each repo runs all their tests through their own dedicated pipelines periodically and report these tests to a shared structured format into a single flaky test detection service. Just to show you the scale of Uber's monorepos, so for Go, we have 122,000 test targets that exist in the repo. We have 3.6 million individual test cases, such as test suites and subtests. And across the other repos, we have 600,000 individual tests that we track as well. And across the different repos, we have tens of thousands of commits that go into the main branch every week. So I'm going to talk about how we report these flaky tests. As mentioned, we built a flaky test detection service that records the history of every test. It aggregates these test results and analyzes the test history to determine when a test becomes flaky and when it transitions back to stable. The service also provides configurable, pluggable analyzers. So depending on the type of test or the repo, how they want to decide a test becomes flaky or not. So in a very simple linear analyzer case, we have if a test fails once in a given window, then the test would be determined as flaky, while if it passes like 100 consecutive runs, then it transitions to stable. In a more percentage-based analyzer case, if a test fails above a certain percentage in a given window, then we can say that this test is flaky, while if it falls below that percentage, then we can say that this test is stable. And this analyzer would be more applicable to integration tests, where we can tolerate more instability. So because they could be making network calls, or it can be spinning up some Docker containers, so it's a little bit more prone to infra failures. And in the end, if a test is flaky, the service would file a bug to the ONI team to make sure that they are accountable for that flaky test. So each repo, as mentioned, has a periodic CI reporting job. It runs all the tests in the repo, usually once every hour, and it parses the Bazel test XML file, which is like in JUnit format, and then it reports all the tests in a shared structured format to the service. And in the repo, the reporting repository CI Flaky test reporting pipeline, we run all the tests in 2 different strategies. The first way, we run all the tests in the repo regardless of flakiness to get the state of all the tests in the repo. And in the second run, we run the tests, all the tests, but skip tests that are flaky. We do this because it emulates the CI behavior on pre-land jobs. So for example, there could be a test, flaky test, that modifies some global state, such as like a shared mock. And if it gets skipped in CI, other downstream tests might be dependent on that subsequent test to run. But then because it gets skipped in CI, then the subsequent test fails. So ideally, this case shouldn't happen. Testers should be independent from each other, but we can't prevent, we don't really have any linters to prevent these shared mocks calls. Oops. So the preciseness of the flaky detection depends on how granular we track the test results. The test results can be tracked from the least to the most granular level. So in the least granular level, we have the Bazel test target. And as we go down the list, it gets more and more granular, such as the test suite or the test function in Go. And the most granular level, we have the subtests or test tables and parameterized tests. So the finer the granularity, the more accurately we can skip the test. And the less granular the reporting, then the more tests we may unintentionally skip. So if you're only tracking tests by the test target level or the test suite level, there could be hundreds of tests or subtests that's under that test target. And if there's only one test that's flaky under that test target, and you're only tracking at the more granular level, you'll have to mark that whole test as test target or test suite as flaky. And by doing that, you might be unintentionally skipping hundreds of stable tests under there. And so ideally, the more tests that we run in CI, the better, more production code coverage. And ideally, we identify exactly which subtest is causing the failure and just skip that in CI. So how do we discover these failing test cases at a more granular level? So Bazel produces a JUnit XML for every test target. In Go, we can provide a more verbose and granular information by setting the environment variable go test wrap test v. But identifying these, the failing subtests can be tricky because we had issues with identifying that the test.timeout in the JUnit XML files, it didn't provide granular level information, which meant that we had to mark the whole test target as a timeout in that case. And in Go, you could have non-deterministic subtest name, which ends up having no history in those tests. So you can set the Bazel test timeout with the test timeout flag, or the test timeout environment variable. And how the test timeout works is for Bazel is that Bazel will send a sigterm signal to the test runner, and it would send a sigkill signal 15 seconds after the timeout. And then Bazel would report this as a test timeout once the sigterm signal is sent. So the original timeout implementation involves terminating the test runner at the timeout, and the issue with this is mentioned there's no post processing, which means that we are losing these more granular test case level information. So the better implementation that we end up implementing is we would pass the test timeout directly to the test runner, and then we would configure the test runner to ignore the sigterm signal to perform a more graceful cleanup and report these partial test results. And then we continue to respect the kill signal because we want to prevent any test from hanging indefinitely. And so then, as usual, the native test runner, if it supports it, already provide this the granular test case and subtest level information, including the duration. So we can parse that test result in format into the JUnit XML format. And because the term signal is ignored, it's possible for some tests to continue to run after the Bazel test target timeout. And any tests that haven't run at this time would basically not have any test results that's reported. So there could be a race condition where we have a test, let's say a test finished at 59.9 seconds, and post-processing of the test result takes another 0.2 seconds. And Bazel sends the timeout at 60 seconds. This means that there could be a discrepancy in the reporting where in the test runner, it reports the test as a success in the JUnit XML file, while at the Bazel test events log, it reports the test as a timeout. Even with this discrepancy, this is still a better implementation because we get this more granular level of information, including the duration of the test at the subtest and the test case level. So we enhanced rules go to report the timeout where we have a number of PRs that report the duration of any of the subtests and test case that completed. We also report the test that was running during the time of the timeout, so any test that was interrupted. And we also record tests that run with t.parallel as well. So this basically allows us to report the duration at the more granular level. So now that we have more granular level information, our goal is to basically disable the slowest subtests. So our approach is basically find the slowest subtest test in the test target definition, mark that subtest as a timeout. But a test suite could have have many slow subtests. So you can imagine that every time we detect a subtest as slow, if there's many slow subtests, this test target could continuously time out in the reporting. So if too many subtests are slow, for example, what we do is if a subtest take more than 25% of the test duration, then we would roll up to the parent test function to avoid the death by 1,000 cut scenario. So this process continues iteratively until the test target stabilizes. So not in terms of non-deterministic test names, in Go you could, the test names could be, the subtests could be non-deterministic because they can be things like timestamps or random numbers. And ideally we don't report these because they won't have any test history because you're essentially generating a new test names every time. And it can cause storage bloat to our Flaky test detection service because we're just sending new test results with a new test name every time. So what we want to avoid sending these test results to the service. And what we do is we would run the test twice with the runs per test flag equals 2. And then if there's any test result that only appears once in the test results, then we can basically assume that these tests are being dynamically named and we should avoid reporting them. And when we find that case, then we would roll up the reporting to the parent level, which would be the test suite or the test function level. The long term, we probably would just want to enforce not having these random generated subtest names. And a test scenario that might escape this situation is a test that name that changes every day. So if it runs today, then we'll probably report it because it's the same test. The test result will appear twice. Well, if it runs tomorrow, it's going to be a different test. Now I'm going to bring it over to Zhongpeng to talk about how we filter flaky tests in CI.
Now that we have a list of flaky tests, the next thing we want to do is to skip them from CI so that they don't give false signals. That's the main thing that we build this pipeline. Because we try very hard in reporting the tests at the granular level, we want to skip them at the granular level as well. And so for Go, we will have to use in order to skip the Bazel the tests at the granular level, we can use a flag called test filter. And for Go, we can pass that test filter, pass a regular expression to the test filter prefixed by the minus. And for Python, it's a different syntax. So we can see that these are the language-specific syntax for the test filter. And in order to do that effectively, we also need to be careful about special characters in the test name because some of the tests can be dynamically generated, like Yushan said. And those special characters can interfere with the syntax. The main problem of using test filter, though, is that the test filter is actually applied to all the test targets that's running by Bazel. And this means that if there are two targets that has the same test case called test foo, then there's no way to skip test foo from one target and keep running test foo from the other target. So what should we do? We have to look at what's under the hood. Bazel actually passed the value of test filter as an invariant variable called test bridge test only to each test target. And the test runner just translates this invariant variable into the language-specific filter. And for Go, it's the combination of test.skip and test.run. For Python, it's the -k for PyTest. This actually opened the door for us to customize the test filter per test target. What we do is that we use builder to set the invariant variable test bridge test only to every test target that has flaky tests. And then we run the test, then those test cases are naturally skipped. But we don't commit those changes because the list of flaky tests change from time to time. And then, as I will cover later, we don't always want to skip flaky tests. Before we take this approach, we explore some alternatives. One common way is to set the flaky equals true for the test targets. This will cause Bazel to rerun the test if it fails. And then there are language-specific ways to skip test cases, like a t.skip in Go or ignore decorator in Java. The challenge of this approach is that it's hard to handle flaky tests differently in different environments. So in Uber, we run those in several different environments. For example, in local environment, we want to run our tests, and we don't want to retry because we want to expose the issue as early in the workflow as possible. In the pre-land blocking job, we want to run the stable test only and skip all the flaky tests. And then there's a post-land flaky test detection job where we run all the tests multiple times without retry. And there are other scenarios. So none of these simple approach will satisfy our requirement or give us the flexibility of dynamically deciding to skip or not. Like I said, there are other scenarios that we actually don't want to skip flaky tests. One common scenario is that when a test fails in a CI, and if the test failure happens at the same project as the changed code, we actually don't want to skip the flaky test because we want to hold the project owners accountable for their own flakiness. And then this also provides a better protection against the regression. One example is that if, say, payment is a project, and there's a flaky test in the payment project, if people change any file in the payment project, then that flaky test will keep running, and any failure will block the change. However, if there's a library owner that update the library or change the library, and that flaky test transitively depending on that library, and so any change in that library will trigger rerun of that flaky test. And in that case, we want to skip that flaky test so that the library upgrade can go smoothly. And some teams actually want to go further. They want to prevent the flaky test from even landing. And so we implement a mechanism to run a test multiple times in the CI if those tests are in the same package as the code change. But this could be costly if we do it naively, because multiple times could triple or double CI time. So we query the test speed data from our flaky test service, and we set the number of runs according to the speed. And for the slow test, we run less time so that we don't delay CI too much. And for the fast test, we can afford to run it more times to increase the sensitivity to the flakiness. And to implement that, we have to first set the flaky test append to 1 for those tests to disable retry, because the retry basically defeats the purpose of detecting the flaky tests. And then we need to run the runs per test. We need to set the runs per test for different tests according to their speed. And if a test is running multiple times in this way, any fail will fail the whole job. And one of the cause of flakiness is actually timeouts. And this is a great percentage of tests marked as flaky this way. And looking into that, we found that some of them are just because they are having too many test cases in one test target. So the first thing that we need to look into is to examine our build files. If we are creating the build file in a project level, then that means it's very likely to have thousands of tests in one target. So the first thing is to create it at the package level, even better at the file level. Smaller test targets allows faster builds and faster tests, and also improve the cache hit rate. However, the smaller test means that more tests will be maintained. And this could be tedious for humans to maintain manually. This is why we need Bazel to automatically update them. But if we are creating tests at a granular level and we still have too many test cases in the test target, the next thing that we can do is to run them in parallel and make sure that Bazel is aware of them. The latter is important because if we run them in parallel without telling Bazel, then that could easily run into resource contention. The one way to run them in parallel is to set the shard count on the target level. And this will ask Bazel to run the test runner in multiple processes. And each process will only run a small subset of the tests. And because there are less test cases in every process, they are less likely to time out. And because Bazel manages all those processes, Bazel is able to allocate the compute resource accordingly for every test process. However, the test sharding strategy will require the support from the test runner. And for Go, the test runner only supports the sharding of the test functions. So we need to set the shard count according to the number of test function. And to know the list of test function, we can pass a test or list flag to the test runner of Go. And setting more shards than the number of test function means some of the shards wouldn't run anything, which is a waste of compute resource. So within one test function, there can be multiple subtests being created. And these are not shardable with the Bazel's test sharding strategy. And in this case, we will have to use T.parallel, which is natively supported by Go, to run them. But because these subtests are running in the same process, teeter parallel basically require more CPU cores for the test process that's running them. So we have to tell Bazel that this test process needs more CPU cores than the default one. And to do that, we have to set the CPU tag in the test target. Over the years, we found that managing flaky tests involve managing the conflicting needs from different people. Library owners find it hard to upgrade their libraries because every time they upgrade, there are many flaky tests failing. But on the other hand, critical service owners, they don't want their tests to be skipped, whether they are flaky or not, because the more tests getting skipped, the less protection their service will have. And engineering leaders are frustrated because people are not prioritizing their fixing of the flaky tests, where engineers don't feel enough support in helping them fixing flaky tests. This is why we ended up designing a comprehensive process from end to end to address the need of different people, and by utilizing the feature of Bazel. We have an engineering blog to introduce more details. Any questions? And we are hiring at our Amsterdam office if anyone is interested.
All right, thank you for a great talk. Well, you can get applause twice.
I had one question. You mentioned runs per test for pre-land detection. How do you decide that a test is either new or that needs to rerun through that assessment with multiple runs per test?
We chose those tests only when they are in the same package as the changed code.
OK, so is it based on like diff and like the version control?
Yeah, so the diff, we have a list of code changes, and then we query the package that the tests that are in the same package as those changes. Yeah.
Thank you.
Yeah, because this is expensive process, we don't want to run too many tests in this way.